So let's start off with the session. Today's session will be conducted by Dr. Peeta Basapati and Supraja. So uh,
Thank you, Abhinav. And as Abhinav has already kind of told, I'll do the easy part of doing talking, and Supraja will do the difficult part of showing you the code and running it. Once again, welcome to the bootcamp, module 2, session 1. This session 1 deals with a couple of things. One is about introduction to supervised learning. So I am just doing some freehand writing so that I don't move very fast. That is the intention. Okay. And under the part of the supervised learning, we'll deal with classification and we'll deal with regression. Now, for people who have already gone through this course, you know that it's almost an entire semester syllabus. Okay. Now, people who are in CSE second year or are in first year, please understand that the number of hours we use for covering these aspects is around 20 or more. However, given the short time which is available to us here, we will give you introduction into some small things such as one or two classification algorithms, how they work and why they work, those kind of things. And out of your interest, you will be able to expand your understanding into other algorithms. You are always welcome to approach me or any of your other teachers or seniors to understand about other algorithms. And people who are in first or second year and who have not got exposed to this, particular program or to the course, will anyway you will face when you come to the appropriate semester. Now, learning is of, so if we look at learning algorithms, first we have to understand what is learning and why is it uh, called as learning, right? So, hmm, see, you have different algorithms. For example, suppose someone asks you to write a piece of code which will take two numbers and it will generate the output of the two numbers. That is addition of two numbers or maybe multiplication of the two numbers. All of you can write this piece of code. And if I want to say that don't make it linear program, but make it more functional in nature or modular in nature, then you will probably define a function where the two numbers are going in after a due diligence on whether the two input values are numbers or not. And they get multiplied or added and result comes back, which you can print it on the screen or you can send it somewhere or things of that nature. This is a piece of algorithm. It may be a very simple algorithm, like almost every student in the world starts with the algorithm of print of hello world, right? There is no learning in it because you have designed how the algorithm is going to behave. It's only the input and the output which gets dynamically determined during the runtime of the algorithm. Whereas in learning, what we do is that we have a general idea about the flow of the algorithm, right? In learning, so what we have are one, we have input and output data. Okay. But we may not know what is the relationship between the input to output data. In the previous example which I gave, I told you that the functional relationship between the input variables which are available is a multiplication operator or a summation operator. Now you have variables which are coming in and you know how to operate on these input data so that you can generate the output data and that you are coding into the algorithm. Whereas in learning, what we have is that we have a whole list of input data. And for each of those input data sets, we have equivalent output values or output data. But we may not know what is the way the input maps to the output. That is, how can we operate on the input data so that the output comes out. So let's take an example from our kitchen. Now, I'm sure 90+% of you, or maybe close to 100% of you, know how to make noodles. So you buy a noodles packet or maybe a cup noodle, heat water, put it into the cup or into the vessel and allow it to soften for next 2 to 5 minutes. Everything is there and then the noodles is ready to be eaten. Now this is like your prior example of algorithm where you take two input numbers and multiply them. A defined procedure is given to you on how to operate on the input so that the output can be generated. Like making noodles. A defined procedure is given to you that take this noodle, open the packet, pour hot water into the cup, close the cover, let it soften for next 2 to 5 minutes, and then the noodles is ready for you to consume. Whereas in learning algorithms, it is like you might have wheat flour, you might have the different ingredients which go into making the masala, but you don't know how to make noodles out of it. So I can give you 5 different examples of the ingredients which are available. And then the five different outputs. One version is a veg noodles, other is veg hot noodles. Okay, maybe plain noodles, chicken noodles, egg noodles, etc. Different ingredients are available. And then you have different output. But you don't know the procedure of how to combine this input through a systematic procedural set of steps so that the output can be generated. That is where we employ learning algorithms. We try to learn how the algorithm can be built by looking at these input data, variables which are available to us, and how the output is getting generated. We make certain assumptions. Okay. For example, I might say that take 1 tablespoon of wheat flour, salt, okay, and maybe pepper or whatever else masala are there, combine them, let it be on the pan for 15 minutes, and then the noodles will be done. Then you do that and you find that there is no noodles here, but some burnt version of some chapati or omelette equivalent has come out. Then you said that, oh, my experiment has failed, right? Then I need to revise my mechanism. or maybe the test was not good. So you keep updating your technique till the time you start perfectly getting an equivalent of a neutral. Okay, that is what happens in the learning. So you look at the data, you look at the output, and you have a procedural state of the algorithm, but you don't know how those procedures have to be acted upon. So you try fine tuning the way the steps are defined so that your output comes out. And you find that the output is matching to whatever was desired, or maybe the predicted output is something which is far away from what is desired. Then you try to fine tune your execution of the steps so that you start getting as close to the output data as possible. That is what happens in learning. Okay. If you have any queries, you can probably unmute yourself and ask. Then let's look at what are the different learning algorithms. Okay. We have at least two types of learning algorithms. One is supervised. Okay. Other is unsupervised. Okay. Let's understand what is the difference between them. Now, sorry. See, for example, recall the days you started going to your school or your learning center, wherever you went first. Some of you might have started learning at home as well. Let's say your teacher or your mother or your father, someone teaches you how to write an A. Okay. Then what will happen? Maybe your teacher will tell you that write A like this. You as a curious child, you understand, okay, the teacher made movement of one stroke like this up and another stroke down and connected the two strokes by a line which is horizontal. That is how A is written. Then you are asked to write the A on your own. When you are asked to write the A on your own, some of you may start making something like this, or some of you may start making like this. Then the teacher comes and corrects you, saying that, hey, this is not how A is supposed to be. You have to join these two vertically slanted lines in some manner. Again, I'm probably using some of these terms which your teacher might not have done, but then that they have to connect at the top end and the bottom ends have to remain separate. Oh, okay. Then you realize that, okay, then my second pattern is not right. The third pattern is also not right. So I have to do something like this and do like this. You learn how to do it. So let's say you went to your nursery school and your teacher taught you this is how you have to write A. You come back and you may have a notorious elderly sibling who wants to make fun of you. The sibling will say that, hey, this is not how A is written. Then the sibling tells you another way to write A. For example, the sibling says that A can be written something like this. Okay. Then now you are perplexed whether this above pattern is A or the below pattern is A. Right? So now what you do is that you approach your mom or dad saying that, see, my teacher taught me that one is A. This elderly sibling who always makes fun of me is telling that the below pattern is A. Now what do I do? Then your next supervision might come from your parent saying that, hey, don't worry, both are A's. And there are many other such variations of A's as well. So now what has happened is that what you learned from your school and what you learned at home have come together to enhance your learning. Thereby, over a period of next few days or few weeks, you have mastered the art of writing A or recognizing A. This is exactly how the supervised learning works. I told you earlier that as part of my data, I have input and output data. Now what I do is that I'll go to the next slide. My input data is, this is my input. This is going into what is called as a black box or algorithm. Okay, it is a black box. Okay, it's a black box. You don't know what is happening inside. And this is basically generating, and let's represent this input as something called as X. Okay. Now it is going into the algorithm, and this algorithm is being acted upon by something like a knowledge base. Okay, this knowledge base will store different parameters and hyperparameters. Let's go back to your prior example of multiplication, that the operator is equal to multiplication, something like that. Then the algorithm will act on this input and will generate your output. Let's call that as Y cap. Okay, this is a predicted value of Y. Now please note what you have in your data set is for every X, like X1 maps to Y1, X2 maps to Y2. This is available with you, and going on, you have Xn mapping to Yn. Okay, you already have n observations which are collected from the world, and equivalent to these n observations like X1, X2, Xn, you have already labeled them what the classes are or what the values are, which are Y1 to Y2 to Yn. When you are taking this X and running it through this algorithm, it is generating what is called as Y1 cap. Because Y cap, because it is a prediction of your Y1 value. Now, since this is a prediction of your Y1 value, now your Y1 cap may become equal to Y1, or Y1 cap may not become equal to Y1. Now suppose Y1 becomes equal to Y1 cap, or Y1 cap becomes equal to Y1. That means you have done a fantastic job. Now suppose your Y1 cap is not equal to Y1. Then there is some error which is created in terms of how you have decided or how the algorithm has acted. Which means we need to refine our steps so that Y1 cap can be as close to Y1 as possible. It's like you taking 1 spoon of wheat flour, 1 spoon of salt, 1 spoon of chili powder, probably 1 spoon of garlic paste, and try to make noodles out of it. It will come out bad. It is going to taste horrible. Then you say that, oh, it became too salty. Let me reduce the salt content. Like that, you continue doing. This is how the learning happens. So which means when I am taking my Y cap and comparing this with my Y value, I am getting some kind of error. And this error is being fed to the refinement of the algorithm. Okay, this error basically leads to refinement of the algorithm, how the algorithm should be updated. And hopefully, as the algorithm means the steps probably will not get executed, but the content in this knowledge bank or the knowledge base will get updated. Hopefully, with the update, what will happen is that next time when you give your X1, the Y1 prediction will become little more closer to the actual observation Y1. This is what is the paradigm of supervised learning. You guys are so far with me? Is my voice still clearly audible?
Yes, sir.
Very good. So now I'm assuming you have done a little bit of understanding of what is supervised learning. Then we'll go to types of supervised learning. Okay. Types of supervised learning. So supervised learning is of two types. Okay. We have classification and we have regression. Okay. Now in classification, what we do is that we follow a approach of bins. These are like bins. Okay, this is your bin B1, B2, B3, or maybe I should call them as categories. Okay, I should call them as categories, and therefore the nomenclature will match better. So this is C1, this is C2. Let's say call them as cups, C3 and C4. Let's say these are 4 cups. Example, if you go into any place, you have trash bins. Okay, there are separate trash bins for dry waste, wet waste, medical waste, etc. Okay, electronic waste, these are separately kept. Now, when you are taking a waste and you want to put it into the bin, you have to make the best decision of which bin should it go to, and you put it only into that bin. You don't try to throw it somewhere in between, because you are not sure. This is a paper plate and that little bit of chutney is left. So I don't know whether it is wet waste or it is dry waste. So I'll put it between dry and wet. It doesn't happen. You make best decision and put it into one of the bins. Okay. So what will happen is that when your observation vector X is coming in and it is running through a classification algorithm, it has to necessarily belong to one of the bins or categories which are predefined and available to you. Okay. Whereas in regression, what we do is that in regression, when your input is going in, it can generate a continuum of numbers. Okay. It's a continuous values. Okay. For example, let's say I measure the height of people who are present in the class. And when I'm measuring height, I might find height such as 5.4, I might get 5.6, I might get 5.7, I might get 6.2 feet as the different heights which are available to me. And using these samples, I build my regression model. Now, regression algorithms allow me to generate values which we have not seen earlier. For example, in this sample set, I don't have a height called 5 feet 8 inches. But my regression algorithm will be able to generate a value of 5 feet 8 inches, even though it was not seen earlier. Because the range is defined to be a continuous set of values. Okay, so your input comes in, it runs through the algorithm, and a continuous output comes out. Okay, now please note, these continuous values could also be discrete. For example, because of my quantization of the values, I may say that I am not entertaining decimals beyond 1 point of decimal. Or I will only take integer values. Then it has to respect that restriction. Now, just because it is generating centimeters like 1, 2, 3, 4, you don't say that it belongs to classification. Understood? So that is the difference between classification and regression algorithms. Are there any questions so far? No, no problem. Then what we will do is that we'll go into our first module here called classification and understand this. So as I told, a typical machine learning algorithms, what happens is that you have your input X, which is going into your algorithm. Okay. And this algorithm is generating as Y cap, which is a predicted output. Now this Y cap gets compared against the available value of Y to generate what is called as error. Now this error could be 0 or non-zero. Okay. Now let's take an example. Suppose what is happening is that you are building an algorithm which will classify footballs and basketballs into two separate bins. So it is like there is a belt which is their conveyor belt to which people come and throw the balls. Football players take the balls, they play outside, and they will come and put it into the same slit which is available. Similarly, the same slit is used by basketball players to put the basketball into it. But in this entire pipeline, your algorithm's job is to identify whether the incoming ball or the given ball is a football or a basketball, and then put them into separate buckets. You may have a bucket for footballs and you may have a bucket for basketballs. Right? Now, suppose your output value is supposed to be football. This is your Y value. Okay. And your predicted Y value is it is basketball. Okay. So now as you can see, this is not matching. So which means there is an error made. Okay. Now, suppose this is basketball and the output is also predicted to be basketball, then it is a matching. That means the algorithm did a good job here. When football was given and it predicted as basketball, it don't do a good job. So we have to keep track of both good jobs as well as bad jobs. Okay. We want to know how many times this algorithm is doing good job, how many times it is doing bad job. Only then we can decide whether this algorithm is a good algorithm or it is not a good algorithm, because there are many, a plethora of algorithms available to me. Okay, I have to choose which algorithm to use. I can't be using all the algorithms because everyone will give a very different opinion. Right? It's like when a new government is formed, every minister has to identify a set of people to advise the minister. Okay. Now they can pick anyone from the state or from the country to be their advisor. If they reach out to 100 people, 100 people will give 100 opinions for a particular issue. For example, our finance minister Nirmala Sitharaman, if she wants to decide whether the tax rate should be increased or should be decreased, then depending on who is asking, they might say increase or decrease. Some might say don't do anything. So you go and reach out to 1,000 people. 1,000 people will give 1,000 different opinions with 1,000 justifications. But that's not how she can run the finance ministry. So what she has to do? She has to go and identify the right advisor whose advice is going to make her run the country well financially. So that is like you going and choosing which algorithm is to be used for a particular scenario. Okay. So you try to decide which algorithm is going to be, and you decide based on how that algorithm is performing on various test data which is given to it. So you throw a football, the algorithm decides it's a football. You throw a basketball, the algorithms decide it's a basketball. You throw 100 such balls and you find that in 95 cases, the algorithm decided that it is a correct decision or it is a right ball. Then you say that 95 out of 100 were correct decisions, right? Now, please note, I am not saying how many footballs or how many basketballs were there. It is only correct decisions. So this means my accuracy of the algorithm is 95%. Okay. Now let's take another example. Let's say your friend is tossing a coin. The coin goes up, it comes down, hits the floor and settles down. Then you find out whether it is head or tail. Now let's say your friend has a special technique by which, by the way the thumb is getting used for throwing the coin up, determines or he or she can control whether it is going to be head or tail. And your job is basically, your algorithm's job is basically to observe how the thumb is getting used during making the toss and predict whether it is going to be head or tail. And you employ an algorithm and you find that 80 out of 100 times the algorithm is able to predict, depending on how the thumb is getting used, whether it is going to be head or tail. Then the accuracy of your algorithm becomes 80%. You are accurate 80% of the times. 20% of the times you are inaccurate. Now let's say you have algorithm 1, okay, and that gives you 80%. And you have algorithm 2, and that gives you 63%. Now which algorithm are you going to use? Okay. Now someone will say it's a no-brainer. I'm going to use 83%. Sorry, 80% algorithm. Why would I use a lower performing algorithm which is making a lot of mistakes? Okay, wonderful. That's a good idea. So you basically choose saying that because my algorithm 1 is performing better at 80%, so I will go ahead and use 80% algorithm which is giving me 80% accuracy on my training or test data. I'm going to use it. Okay. So this is how you decide which algorithm to use. And there are other performance metrics, for example, precision. Okay. And we have recall, and we have F-score. Okay. We have area under the curve, different other things are there, which are strictly used for classification algorithms. Now, please note, this discussion is for classification algorithms. This doesn't apply for regression. Okay. So the different metrics we use for measuring how an algorithm is performing in classification is we use accuracy, we use precision, recall, and F-score. I have explained to you what is accuracy, and if time permits, we'll discuss about precision, recall, and F-score as well. Otherwise, you can do a little bit of study on them, and then you can also learn how to use them. So far what we have discussed what is learning, what is supervised learning, and within supervised learning, we have discussed about classification and regression. We discussed about what the difference between classification and regression. Okay, so when you have to take a decisive step of putting it into one of the categories, it is called classification. And then having decided that you have a classification problem, you have many different algorithms. Now, how to choose which is the right algorithm to be used for your particular problem statement? That is using what are called as performance metrics. Performance metrics. These are accuracy, okay, precision, recall, F-score, etc. and etc. Now let's look at one or two of these algorithms. There is a very, very simple algorithm which is available to us. That is called as ANN algorithm. What does NN stand for? NN stands for near neighbor. Near neighbor. Okay. Now let's take an example. Suppose you are doing a travel in train. Now in train, many people board the train at many of the stations, and many people alight at many stations. So train is like a dynamic wagon where people are coming in and going out. And let's say you are making a long journey, something like from Bangalore to Delhi or to Bangalore to Guwahati or somewhere where you are spending substantially large amount of time being in the train. Now, imagine I am one of the TTs, the train ticket examiners. I find that you have started spending a lot of time with one guy, okay, or one particular person or family, and then you are talking a lot amongst yourself. Probably you are also having lunch and dinner together, and all that is happening. And I don't know which area of the country do you belong to, but I know that of your neighbor. I know that your neighbor comes from, let's say, Indore in Madhya Pradesh. So what would I do? Because you are spending a lot of time with a particular person who is from Indore, so it becomes natural for me to assume that you are also from Indore. If we are looking at classifying you based on locality. Now suppose in that train there might be teachers, there might be students, there might be clerical staff, there might be doctors, and there might be software engineers. Now you may spend some time discussing with each one of them, but possibly you will spend a lot of time discussing about how your job is going, how is the job situation evolving, etc., with another person in the same profession. So if I were to classify you based on your profession, I'll see with whom you are spending a lot of time. Okay, and then I try to put it into that. Or it might be based on your hobbies. Okay, so let's say it's a sports wagon. A lot of sports people are going. And if you play a lot of cricket, then it is most likely you will start interacting with other cricket players rather than with tennis players. So the principle is we identify your neighbors, your test observation. We identify your neighbors for whom we know already their categories or levels, class levels. And then we try to put you into your level. So here what we are doing is that imagine a situation. Let's say we have your feature F1 and we have your feature F2. And let's say these are some green circles who belong to one class. They are cricket players. Okay. And then I have some red crosses. Okay. Who are like tennis players. And so I know the green circles are cricket players. I know that the red crosses are tennis players. And you are like this blue triangle. This is your test. For whom I don't know whether you are a cricket player or you are a tennis player. So what I'll do, I will try to identify, okay, something like, I'll try to find out how far or how much time you are spending with your neighbors. Okay, this is my distance measure. More time you spend with someone, less is the distance. Like that. Okay. And then I find that this particular pattern is someone with whom you have spent a lot of time, which means you are very close to this person. Okay. So it means my distance is less. So the minimum distance neighbor. Okay. Or it is called as nearest neighbor. Okay. So now I know that your nearest neighbor is a cricket player because it's a green circle. So I say, because the nearest neighbor is a cricket player, so this fellow who is my test pattern is also cricket player. Okay. So this is how the nearest neighbor algorithm works. So here it is NN algorithm, nearest neighbor, NN algorithm. Understood? Now what happens? See, you might be a cricket player, and then in the train when you are traveling, you find that there is a pretty charming guy who is doing a lot of nice talking. Okay. And you might be a tennis player, but you are attracted to this guy. Okay. Because of some other attribute, some other reason. So what happens is that you go and start spending a lot of time with this cricket player because you find this particular cricket player to be very attractive and very friendly. Okay. Now, just because you started spending a lot of time, you are still a tennis player. It doesn't make you a cricket player. So sometimes what happens is that if we are trying to base our decision based on only the nearest neighbor, we might make mistakes. Okay. So what we will do is that, however, if I find that you are spending a lot of time with many cricket players, then it is very likely that you are a cricket player. But if I find that, okay, You are spending the most time with this particular guy who is a cricket player. But then you are interacting with a whole lot of time with other tennis players. Then I said that, okay, this interaction with the cricket player is probably some outlier. Okay? Outlier means some noisy pattern, some anomaly, some not regular way of doing it. Some other factor is influencing it. So I cannot decide based on only your interaction with this guy. I have to look at who all other are you interacting with. So that is where we come to KNN, where K is greater than 1. Okay. So let's say K is equal to 3. So what I do? I basically try to find that you are interacting, one is with this guy, then you are interacting with this person, then you are interacting with this person. There are these 3 people with whom you have interacted. Okay, most you have interacted with these 3 people. Now, if we look at this pattern formation which has happened, you find that amongst your 3 near neighbors, okay, so I am taking K is equal to 3. Amongst the 3K near neighbors, you have interacted with 2 cricket. Okay, so let me erase the word cricket. Okay, let me say 2 cricket players and 1 tennis player. Okay. Now, because you have interacted with 1 tennis player and 2 cricket players, so which means amongst these people when I am doing a voting, I find that you are interacting with cricket players more frequently than with tennis players, which means this should belong to, cricket player. This is a voting. Okay. How many members present? Total 3 neighbors. What is the dominant class in these 3 neighbors? Cricket. So they win. It is like our parliamentary democracy. Each party has the majority presentation in the parliament, they form the government. Equivalent here. In the neighborhood assembly, whichever party or whichever category dominates, they basically win the test pattern into their category. This is how the KNN algorithm works. Now let's recap. You have observation vectors like X, which are collected, they come in. Then you equivalent to them, you have your Y values, which are like either categories or values. And you try to learn the algorithm in such a manner that the algorithm gets tuned. After that, what you do is that you try to evaluate the performance of this particular algorithm using metrics such as accuracy, precision, recall, F-score, etc., and find out which of the many algorithms is performing best. And then once you have identified that algorithm, you take it and deploy it. Now the question is, how does the algorithm work? And for that, we take an example of a KNN algorithm. There is another algorithm. Now this KNN algorithm works best. Okay. Let me call you have something about KNN. Now KNN algorithm works on distance principle. Works on distance principle. Okay. And we can use any distance. For example, let's say Euclidean distance. Let's say you have a vector x1. X1 is consisting of many attributes x1 going up to xn. These are one. All. And you have another vector x2, which is equal to x21 going up to x2a. So how do you find what is the Euclidean distance? So the distance between x1 comma x2 is equal to square root of sum over all dimensions. Okay, I is equal to 1 to m x1i minus x2i. You square it because sometimes the difference could be positive, sometimes they could be negative. So when you square it and you add it, you get the squared sum of differences, and then you take the square root of it. This becomes your Euclidean distance. Now using this distance as a measure, you go through all the different data set, training data which is available with you for the test data. So you take your test data and start measuring your distance with all the training patterns and find out the neighbors. And once you have found the neighbors, you take their voting of which class is dominating in the neighborhood, and accordingly you assign this thing. Now please note, because you are operating on the principle of distance, let me use a different color. Because you are operating on the principle of distance, it will work only when your xi are continuous values, continuous numericals. Okay, numerical or numerals. Now suppose I say that you are a boy or you are a girl, gender or sex is one of the attributes. Now I cannot calculate distance. If you put the state you are coming from, now that also cannot be used for calculating distance. So either you convert them into numerics by employing different techniques which might have been taught in your previous module, or you don't use KNN for such kind of data. Okay. Now there are situations where you have, okay, let's assume X vector is consisting of only categorical data. Okay. For example, your height, whether you are tall, medium, short, your weight, whether you are heavy, average, or lightweight. Okay. The state you are coming from. Okay. And how much study you are putting in for your exam. We'll put that as large, good amount of study or high amount of study, average amount of study, less than average amount of study. So these are all categorical data. Nowhere I have a number. So when I have such data, what I can do, for example, let's take a data set. You have observation, and we say height as your attribute, and then we have weight as your attribute, and we have study as your attribute. Okay, and finally, whether you are pass or fail. So we say observation O1, height is tall, weight is medium, study hours is average. So you have pass. Observation O2, height is average, weight is heavy, study hours low, you fail. And so on and so forth, we have data. Now, as you can see, for such kind of data, we cannot calculate distance. Okay, but what we can do is that we can build a tree. For example, you are starting at a root node, and let's say you are assuming height as your criteria. So you can say that height is, I have three things. One is tall, then we have medium, then we have, sorry, tall, average, and we have short. Now, whatever tall people are there, they belong to this. Now, again, I can say study hours. Okay. I'll take height here. And study hours. I can say whether you have studied is high, average, and low. So these are three different nodes I get. I can go on doing. And as I go on expanding my tree, at some point of time, I'll find end states. Okay. And these end states will tell you whether for that kind of data tree split, whether you are a pass or you are a fail. So such a decision making, tree based decision making algorithm is called a decision tree. Okay. So what you are doing based on a particular attribute or a feature, at each point you are deciding whether it belongs to this path or that path, and it goes on expanding. Finally, you are able to define whether this particular observation is a which bucket it belongs to. It's like you are defining a if condition with a lot of conditions. For example, you say if height equal to tall, study hours is equal to high, and weight is equal to medium, then pass. Else if height equal to tall, study hours is average, and weight is heavy, then pass. Like that you go on defining. So the algorithm works this way. But a visual depiction of that is in terms of a tree structure. And such a tree is called a decision tree because this tree is helping us arrive at a decision on the class value for an observation. And when by some mechanism we have created a lot of such trees which are running in parallel. So I have an observation which is there. Let me go to the next slide. So I have an observation X which is coming in. Now it is going into, this is my tree T1. Then it is going into tree T2. Then it is going into third tree T3. And similarly, it is going to, let's say, tree K. K may be 100 or 500 or something. Now each one of them will give me a decision, right? Y cap 1. Now this will give me Y cap 2. This will give me Y cap 3. This is my Xi. So this is I, this is I, this is I. And finally, I'll get a decision from here as Y cap I K. Now I have so many decisions coming from each of these trees. So what I do is that again, I employ the same principle of KNN. On that, we do voting and finally decide my Y cap for I based on voting. Okay. This is the principle called as random forest algorithm. So as you can see, random forest is nothing but a set of randomly constructed trees which are operating in parallel, and finally by mechanism of voting based aggregation, we are arriving at a final decision for the observation pattern which is coming in. So this is called random forest algorithm. Okay. Now it has been little more than 1 hour since we started, and let's do some practice. I'll hand over the session to Supraja, who will now run you through the practice session. Please work with her, run through these algorithms. Some of you may already have, like, people who are in third year, or second year AI, you might have already done all these things, but that's okay. Still run with her. Okay. And experience it so that you learn the classification algorithm. The practice session may continue for around, let's say 30 to 40 minutes. And after that, we'll start with the regression algorithm. Supraja,
Thank you, sir.
if there are any questions, you can feel free to ask.
Yeah.
Or if there are no questions, we can continue with the session.
Good morning, all. I'm Supraja. So I will be running you through the practical implementation. Let me share my screen.
Supraja, just 1 minute.
Yes.
By the way, guys, while you run through the practice session, if you have any queries, you can post it to the chat. Okay, and I'll address all of them. Okay, Supraja, over to you.
Yes. I hope my screen is visible. Yes. So first, since sir just recently covered KNN, now we'll go through KNN. So I have a data set which is the placement data set which I've taken. I will just show that data set 1 second. So this is the placement data set. I got this from Kaggle. So we have the student ID, CGPA, internship projects, workshop, aptitude test scores, and all these things. So this is basically a classification task. So we need to find out whether that particular student is placed or not placed. So we have imported the required libraries, and I hope everybody is aware of these libraries, right? Should I run through any of these libraries? Anybody? All these libraries are clear, right? Pandas, why do we use pandas? Pandas are used for handling the tabular data, NumPy for mathematical operations. Then we have the matplotlib, which is for the visualization. And then we have the train test split. Basically, we have to split the data into train and test. So we have imported that from sklearn. Sklearn is basically a machine learning library, open source library, from where we can we have to import all these for our model.
Supraja, one
Yes.
question I have. Is this code given to them in some place from where they can take it?
I need to check with Abhinav, sir. Abhinav?
Sir, we'll be posting this code on the website. So there they can find it.
Because it is lengthy code and typing and everything is probably going to take a lot of time. What I would suggest is that why don't you post it into the place where they can take it and run along with it.
Okay.
We'll do fine tuning of the parameters as we go. Okay.
Yes,
And
sir.
they can always refer to it or they can write their own code as well.
Yes, sir.
That way it will save time.
So do I share it? Abhinav, where do I share it?
Right now you can share it in the chat. We'll later put
Okay,
up in the website
got it. Yeah.
after the session.
Okay. Yeah. Yeah. So I have shared you this thing, a notebook and the data set. You guys can upload it in the GitHub, sorry, not GitHub, in Colab, and you can run it parallelly. Yeah. So shall I continue? I think my runtime got disconnected. Yeah. I hope all of you are with me, right? Shall I continue? I'll continue, right? Answer,
Yeah, please
guys.
continue.
Are you all there? Yeah. So I think, yeah, so I was telling you this sklearn. Yeah, then we have the standard scaler. We want to standardize the numerical features. That is, mean is 0 and variance has to be 1. So we are standardizing it because we want to improve the model's performance. Then we have the k-neighbors classifier. That is what we are going to explore. And then we have a pipeline. I will explain about this pipeline shortly, but I'll just give you a gist. So what this pipeline is basically, it will help us in combining multiple steps. Like we want to do scaling. At the time, we want to implement the KNN algorithm. So in a single pipeline, we'll be executing that. That is it. I will be elaborating on that, don't worry. And then we have the metrics, accuracy, score, then the classification report, which will contain precision, recall, F1 measure, all those stuff. And then I'll also be showing you the confusion matrix. And then we need to, for visualization, we want to see how the recession boundary has put down both the placed and not placed. So very first step is basically loading the data set. So this is the placement data set, which I had shown you earlier. df.head, the first five this thing instances will be displayed. As you can see, this is a student ID, CGPA internship, and all other features and the are mentioned. Now, df.info basically will give us the all the information, basically the data types, everything. You can see student IDs, integer. Then we have the CGPA, which is float, because and then we have the shape that this data set is basically 10,000 10,000 rows and 12 instances, 12 features. And then df.describe will basically show us how it is, how it is in the 25% quartile, then 50% quartile, and 75%. And then I wanted to show how the data set is distributed. So if we see that 4,197 students are placed, and 5,803 are not placed. So the 0 refers to those students who are not placed, and 1 refers to the students who are placed. So you can see the distribution of the placement status. Then we have numerical features. So I think you could see over here whichever are the numerical features. We have these numerical features: a CGPA, internship, project. CGPA are the number, internship, whether the student has done 0 internship, 1 internships, or 2 internships. Then the number of projects they have done, this number of certifications they have done, what is their aptitude test score. So these all are the numerical features. So I wanted to visualize how each of these features are there. So basically, this is the thing. So you can see the students 6.5, the students who lie in the range of 6.5 CGPA. Then the number of students who have done 0 internship, 1 internship, and 2 internships. Then we have the distribution of the project. Then the number of workshops they've been attended, and then certifications, then the aptitude test score, and all those things. So basically, it's all the uh, distribution of all the numerical features. Next, these all are pre-processing. I think you guys would have covered it, but this is a subsequent step. Then only we can come to the models evaluation. Next, we're checking for missing values. We can't just ignore the missing values. If the instances have missing values, it will affect the model's performance. So we're checking for the missing values. As we can see that there are no missing values. Then we had converting. Now we have the some categorical features. So now what are we supposed to do? So these categorical features, the machine can't directly understand what to directly how will it deal with categorical values. It can't. So we are supposed to convert it into numerical this thing. So what we'll be doing is, so those students who are placed, we are assigning them the value 1, and those who are not placed, we are assigning them the value 0. That is it. And then we have extracurricular activities. So if you see here, it's no, yes. So again, we can map it to 1 and 0. So those have done extracurricular activities, we can just give them map them to 1, and who have not done any extracurricular activities to 0. Then the placement training, if you can see. So the placement training, again, it is no yes or no value, a categorical value. So we're just converting them. So we're mapping those who have had placement training to 1, and those who haven't had placement training to 0. And then we are splitting the data. Till anybody has any questions anywhere? All good? Any doubts in the pre-processing steps? Anybody? How we have handled the missing values, how we have displayed the data. Anybody has any questions? Okay. Yep. So now what we'll do is, now we have to split the data. Now how are we splitting the data? So why are we doing training and testing? Anybody? Why are we doing training testing? What is the need of training and testing? Why is training and testing necessary? Anybody? Come on, guys, be interactive. No answers? Okay, I'll let you guys know. So why is training necessary? So training basically will teach the model. Training will teach the model, and testing will basically evaluate how well the model generalizes to new data. So if we do the training on all data, then we can't measure on the unseen data, right? So you have to see, now I'm giving an image of cat and dog. So if I give the whole 100% to training, then I can't evaluate. I don't know how well it is performing. I don't know how it is generalizing. So we have to do training and testing. So we have done in training is done on the majority. Why? Because if because ML models can't learn, because something has to be major. So we will it has, if it is in the lower ratio, then it will basically evaluate poorly. So the training data set has to be in the majority portion, and the 20 set is basically on the unseen data. So that is why I've done training and testing. So we have from sklearn, I had showed you already, we had imported this thing. So we are just splitting the data into 80-20, and then random state is equal to 42. Basically, this is for reproducibility. This would have been covered already. Next is the way standardizing the feature. As I told you, that the mean has to be zero and the variance has to be 1. So we are doing this because we want the data to be scaled. Like if we want to prevent features with large values. So if we have CGPA is 10 and internship is 2. So basically, CGPA is dominating. So we don't want it in that range. And why standardizing is important is because KNN uses distance calculations, and if one feature has a larger value, it can dominate the distance metric. So scaling basically ensures that all features contribute equally. Next is we are training training the KNN classifier with full features. Now, I mentioned this pipeline. Why do we use pipeline? So basically, why do we use this pipeline is because a pipeline is like in a machine learning. In machine learning, we use it because we want to automate the workflow by combining multiple pre-processing steps. So now, if I hadn't used pipeline, I had to standardize it, then I had to fit, transform. But pipeline just does it in a single step. I don't have to manually transform the data by scaling, feature selection, then fitting, and then transforming. All those steps is unnecessary. So just if I do pipeline, it will be done. So we have scaled it, and then KNN, K nearest neighbors, where this is the classifier which we're using, and I've instantiated the K to be 15. So the K n neighbors which I've taken is 15. Now then I am selecting the features. Now I want to visualize. I want to see how well I want to see the visualization for internship and project. So if a student has done multiple projects which are valuable, so it is definitely that he would get internship, right? So I have taken that relation. It can also be an internship versus CGPA categorization, but here I've taken an internship versus project visualization. So the selected this thing data frame internship and project. So the target variable is the placement status, whether the student has been placed or not. So we're going to see that. After that, I am training the KNN model. So pipeline scalar, this we are scaling it, and then this all is done. The whole, I told you we can bypass the step, that is instead of fitting, transforming, all those steps are being cleared in pipeline. So for the n neighbors we are doing, I'm 15, I have assigned the value here, which is 15 for the 15 neighbors, and weights is equal to distance. So now what is this weights equal to distance? Again, sir would have already told that basically here I will be using Euclidean distance, but here I can't use Euclidean distance because it's a classification task. It's not continuous values. Here in my case, what I'm doing is I'm using distance here for classification because model doesn't predict a continuous value. Instead, it assigns a class variable. So I can give an example. Suppose here I have a neighbor. So basically, these three neighbors, I have k equal to 3, whether I'm checking whether the class is placed, the first neighbor is placed, second and third are not placed. The distance, like their distance from that particular neighbor is 0.512, and weights is nothing but 1 by the distance, 1 by 0.5, that is it. So now what I'm trying to, what is the inference I'm trying to make here is, now if I sum up the class votes based on the weights, so basically the placed total weight, suppose here is 2, and not placed is basically 1.5. Since placed has a higher total weight, that means the model will predict that placed for this particular student. You get my point? I'll repeat. So what I'm trying to say is basically we have a new student. So what is this? What is this small prototype which I've taken is I'm whether classifying whether a student is placed or not placed. So suppose we have a new student whose placement status needs to be predicted using KNN equal to with K3. Value K is equal to 3. So I have first neighbor, second neighbor, third neighbor, and their corresponding classes, whether the student is placed, not placed, and their distance. And then the weights. Weights is basically, as I told you, it's just 1 by distance, 1 by 0.5, 1 by 1, 1 by 0.5. Now I'm summing up the class votes based on the weights. So the placed is basically, placed total weights is basically only 2. You can just see it's only 2 over here. And the not placed is basically 1.5, 1 plus 0.5. Since placed has a higher total weight, the model predicts placed for the students. So basically now why is this useful? Basically, it will handle the class imbalance better. So if more faraway points belongs to a dominant class, they won't overpower basically a closer but a rarer class. So now one typical question which will arise in your mind is, what happens if a distance is 0? What happens if, suppose, this distance over here is 0? If this is 0, so if a neighbor is exactly 0, the same, so 1 by 0 is not possible, right? I'm saying that like here, if I put instead of 1, if I put here 0, then here 1 divided by 0 is not possible. This also, I'll assume that this is also 0. So 1 by 0 is not possible, right? So 1 by 0, so if a neighbor is exactly the same at the query point, it will get infinite weight because 1 by 0 is undefined. So in this case, the model will directly assign that class without considering the neighbor, it will directly assign it to the other neighbors. So that is the case. So now we'll continue. Now I am making the predictions. So now I'm evaluating the model. So I'm printing the accuracy for this KNN. So accuracy has turned out to be 0.747. So now accuracy, with only just accuracy, we can't, that is not the only metric which is being used. So there are other metrics also. That is why I have brought in the classification report. So this classification report gives us the details about the precision, recall, F1 score, support, and all those stuff. Now we can see that now for the class. So now let's see about the precision first. So for is not placed, for that is for the zeros class, what it has done is 0.77. So when the model predicts not placed, it is correct 77% of the time. I repeat, that is when the model predicts not placed. So we are looking for 0 is the not placed class, 1 is the placed class. So now for 0, if I see, it is 0.77, the precision. That means when the model predicts not placed, it is correct 77% of the time. Now when I come to 71, that is for the placed one, when the model predicts placed, it is correct 71% of the time. That is what precision is. Now when I come to recall. Now what is this recall? Recall is basically, it is for not placed, it is 0.80, right? So out of the actual not placed students, the model will correctly identify 80%. Now when it comes to 0.67, it is basically out of all the actual placed students, the model correctly identifies only 67%. That is recall. Now, when we see F1 score, basically it's a balance. F1 score is a balance of precision and recall. So for not placed, it is 0.7, and for placed, it is 69%. So since F1 is lower for the this thing, for the placed this thing. So the model struggles more with the prediction placement correctly. If we see here, this is lower, right? For the class 1, it is lower. Then this is the total instances we have. Then if I have to talk about the confusion matrix. So the confusion matrix here, everybody knows in the diagonal we have the true positives. The first is the true negative, then we have the true positive, then we have the false positive, then we have the false negative. So here, if we see the model correctly predicts not placed student for 941 students. It is actually true, and also model also correctly has predicted that it is 941 students who are not placed. Now let us come to the this thing, false positives. False positives are in 231 in number. That is, model has predicted them as placed, but they're actually not placed. You get it? That is, the model has predicted them, they are placed, but actually they are not placed. So that is called false positive. When I come to 275 are the false negatives. That is, model has predicted them that the student is not placed, but actually they were placed. That is it. Next, when it comes to 553, which is the true positive, that is, model has correctly predicted them as placed, but in reality, the model has actually predicted them they're placed. So they are correctly has it has model has predicted. So this is the true positive, that is, a model has correctly predicted not placed. Then this is the true positive, that is, model has correctly placed that 543 students have placed, and in reality also 553 students are placed. When we come to this thing, this is a false positive, that is 231 students where model has predicted they are placed, but they were actually not placed. When it comes to 275, the model predicted them not placed, but they were actually placed. That is the confusion matrix. Hope it is clear. Now the decision boundary. So let us first look into this, then we'll make inference. I'll talk about the code. So first thing what comes to mind is the color, right? So you see two different colors over here. So basically the yellow color, if you see, the yellow region is basically the placed students which are placed, the class 1. So if a student falls in this particular region, based on their internship and projects, they are most likely to be placed. That is what is the inference for the yellow region. Now, let's come to the purple region. So this purple region basically tells that students are not placed. That is the class 0. So if a student particularly falls in this particular region, they're less likely to be placed. So now what, as I told you, I had taken a visual, you guys can take, so you guys can make an inference for anything. I have taken internship and projects because I thought like if a student would have done more number of projects, he would have had more exposure. So I wanted to make a visualization. You can also take internship and CGPA. You can make an inference. For my particular use case, I have taken internship and projects. So yellow, as I told you, yellow region is basically for the placed students. So whoever falls in this particular region are most likely to be placed, and whoever falls in the purple region, basically the student will not like less likely to be placed. And one more thing also, you can make an inference, that is, if a student has more projects, high placement chances, that is the upper portion of this particular plot, that is predominantly yellow, right? Suggesting that like we have more projects means the likelihood of placement is also going to be there. Now, when we come to this particular region, if we see, it's a high risk of not getting placed, because the lower left portion, if you see over here, is mostly purple. That is indicating that the students with fewer internships and projects will struggle with placements. So that is that. And then we have this like a balanced region. Some of them are there here. Like even though like this yellow is should like it's misclassified, but no, it's like only in a minority portion. So now what will we do the balanced region? That is basically some areas in the middle portions around 1 to 2 projects. Like basically they will show a mix, meaning the placement can either be depending on the other factors also. That is also there. Here I've taken the k value to be 15. I had already told you. So the decision boundary here, if you can see, it's relatively smooth, indicating that the placement classification is influenced by multiple surrounding data points and all this thing. But if we are now here I've taken k15. Now if I let's experiment. If I take a lower value of k, then it is going to be like this thing classification is going to be different, right? So I can show you. If we let's take a different value of k and experiment with it. Let's take k equal. Now, you can just have a visualization, like you can check. If here, except this point, it has correctly done. Now, let's change k value. It will be a little bit haphazard. Let us experiment and see. So I'm taking k to be 12. Let's take k to be 12. So let's run everything again. Look at this. Here. It is fine, not bad, but again, we have here a little haphazard this thing. Let us put a lower value of k and check how it performs. Okay, you guys can see how it is doing. So basically, it's based on its neighbors. It is trying to allocate the decision boundary. So I will just run through this code how we have done. So basically, I've just created a figure axis. So I wanted it to be in 8 to 8 commas this thing, and then decision boundary. I've imported this thing, and then we are doing the prediction. The color base, basically, I told the lighter color to be the class 1. That is basically those who are placed, and the purple color is basically for the place 0. Then the points are the scatter points. Right? That is it. Yeah. Any doubts over here? Anybody? Any doubts in the visualization or any part? Okay. Sir, should I go through the other models, the SGM?
Supraja,
Yeah, Abhinav?
someone is asking you to explain the confusion
Yeah,
matrix
sure,
again.
sure. Yeah, yes. Okay. So where is, yeah. So we have this confusion matrix, right? Okay. So you guys, do you know the formula for the confusion matrix? Okay, I will write it down in this. Yeah. So, yeah. Yeah, so what is the TN value? So if true, first I'll talk about this, then we'll come to the other thing. Okay. So let me take the values. So it is 972 and 490. So this was 972. This was 490. Okay. Yeah. So now what is this basically? This TN, what it tells us is basically the model has correctly predicted not placed. It has correctly predicted the not placed students, and actually also they were not placed. So that is not a TN. Now what is TP is model has correctly predicted. Model has correctly predicted the students who are placed. So this is this. The model has correctly predicted that 972 students are being placed, and then for true positive, it is model correctly predicted the placed students. Here it was the not placed students, and here it is the placed students. Now, when it comes to false positive, so false positive is basically like, let's take an example. Suppose 230 students uh, were in this region. So that is model had correctly placed, they were placed, but in reality, they were actually not placed. So this FP basically tells us that, so FP suppose value is 230. So if this is 230, it basically tells that model has predicted that these 230 students are placed. Model told that these 230 students are placed, but in reality, they are not placed. That is FP. Now let's take FN, false negatives. So false negatives, what is that is? False negatives are, suppose let's take another number example, 275. So model has predicted that these 275 students are not placed, but in reality, they are placed. That's it. Is it clear at this? Is it clear? Anil, is it clear? Anybody else, any doubt? Any part of the code, anywhere, pre-processing, pipeline? Abhinav, should I run through the other models?
I think we should go with regression first. Then, if time
Regression.
permits, we'll go with
Okay.
other models too.
Yeah, regression sir will be teaching or the code, practice code?
Sir,
Sir?
Yeah.
would you
So
like to start off with regression?
let's give them some 10 minutes for them to go through the code. People at least like, the speed with which you moved. Let them just go through it and
Okay, yes.
make themselves acquainted. We'll start the regression at 11:45. If they want to take a break or go through the code, acquaint themselves or something of that nature, let them do it. Shall we continue?
Yes, sir.
Thank you. So I won't take a lot of time, probably take around 15 minutes to complete. Give an introduction into regression, and then Suproja would again need a little more time for showing her regression related solutions. So as I have said, regression is prediction for continuous values. Obviously, the output cannot be categorical data. It has to be a numeric data. If it is categorical data as output, you better employ a classification technique rather than a regression technique. So for example, again coming back, let's imagine a situation. Okay. And I'm sure since most of you were born post 2000, you would have gone through your vaccination charts and you would have seen very interesting kind of curves which are given at the end of the vaccination chart. Okay. For example, suppose you have the weight of a baby. Okay. It's a baby's weight. Maybe in terms of pounds or in terms of kilograms it comes. And then there is this height. Okay. The height may be in centimeters. Okay. And weight may be in kg or pounds. Okay. So what you will find is that if you look at the vaccination chart, you will find that the curve follows something like this. Okay. As the weight grows, the height keeps growing, and probably after some time, you will see that the height saturating or something of that nature. But it's not a straight line. You will find a band of values, something like this. So this is the band which is considered to be the normal band of values, which means the child's weight. Now the chart could be reversed in the sense that the height and weight might be appearing on the different axes. So here, as we see, we are saying as the weight keeps on increasing, the height increases. And height is in centimeters, which is a continuous value. And weight is in kgs or pounds, which is also a continuous value. Right? Now, in the regression terminology, the weight is independent variable. Okay. And height is the predicted value or dependent. Dependent value. Okay. So you would have seen, and this is one, right? If we look at another situation, what may happen is that suppose we take an example of your placement thing, whatever she was saying, right? Let's say your CGPA out of a 10 scale is this, and the salary offered is the dependent variable in, let's say, LPA, lakhs per annum. So what happens is that as you go on increasing your GPA, so these are different parameters, so observations, right? Sometimes it can go here, 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 like this. There are different observations might be there. Right? As your GPA increases, the salary offered to you was an increasing. In a situation like this, we may say that I'll be able to draw a straight line, which will be able to tell me or functionally represent the relationship between the independent to dependent variable. Now, in a situation like this, what we will say? Now, suppose one student comes to our CIR department and says that, see, by end of my fourth semester, my GPA is, let's say, 5.4. Can you tell how much of salary am I likely to draw? Then the HR person, sorry, the CIR person might be able to make a mapping and say that, okay, this is the potential salary is what you will draw. Okay. Or another example I can give is, let's say I say, this is temperature and this is kilowatt hours of energy consumed. This is energy demand. Okay. So as the temperature goes on increasing in the campus, the amount of kilowatt hours of energy we draw from the grid, the BESCOM grid goes on increasing. So as the temperature goes on increasing, okay, we start drawing more and more energy. So we may say that we also have a straightforward linear relationship between the temperature and the energy we draw from the grid. Now, based on the weather forecast, if the weather forecast says that this summer the temperature is going to be around, let's say, 33 to 37 degrees Celsius in Bangalore throughout the month of April, then I can use this to calculate how many kilowatt hours of energy the campus will draw from the grid. Accordingly, it can be used for estimating or budgeting the electricity bill for the campus. So these are the different scenarios and use cases where we can use regression. Now, as you can see, I have drawn some straight lines and there is another place where I have a non-straight line as well. So if we are trying to do this functional mapping through a straight line, okay. So if function is represented as straight line, we say it is linear regression. Okay. If function is non-straight, so we may use like something like polynomial regression or some other forms of regression. Okay, so now let's look at linear regression, assuming that the function can be represented as a straight line like in the previous two graphs. We try to create the straight line mapping. Now, all of you know, this is from your high school maths, that for a straight line, the equation for a straight line is represented as y is equal to mx plus c. What is m? M is basically the slope and c is the bias or shift parameter, and x is my independent variable. Somehow it is not coming out this way. Okay. Independent variable, whatever. And y is my dependent variable. So these are all known. Now in your mathematics, you would have said that, okay, given m and c, for a given value of x, find y. This is algorithm. For machine learning problems, what we have is, we have set of x observations and we have set of y prediction targets. Our job is basically to estimate the values of m and c. Okay, because we don't know what is m, what is c for ML problem, and those are called as parameters for us. So we'll revise that formula and write it as, now y cap is equal to something like theta 0, which is equivalent to c, plus theta 1 x, and y is equal to y cap plus some finite amount of error. Okay, so you can say y is equal to theta 0 plus theta 1x plus some error, some amount of error. The job is basically to find, I'll put it in a different color. Okay, find theta 0 and theta 1 such that this value is minimum, and it is not for one observation but over a set of observations. This is minimum. Okay, that is the problem of regression. Okay, so once we find our values of theta 0 and theta 1, we will be able to use it for prediction. Now again, let me touch the performance metrics. Problem is happening. Performance metrics. We did a lot of discussion about performance metrics for classification. In the performance metrics for classification, we discussed about accuracy, precision, recall, because you have a target value and you have a predicted value. The predicted value either matches to the target value or may not match to the target value, depending on your parameters get calculated. Now, when you are predicting a continuous value, it is very difficult to say whether it matches or mismatches. For example, suppose you are predicting the energy consumption for the entire month of April in the Amrita Bangalore campus is to be, let's say, 10,000 units. Okay. So prediction is 10,000 units. And actual, after month of April is done, when you find out how many units were consumed, you find that it was consumed 10,211 units. Okay. Now you cannot say the prediction was entirely wrong, nor can you say it was correct. what we can say is that our prediction was almost close to what was actual, with some error. So now the question is, how do we measure this error? So as you can see, we have the actual as y and we have the prediction value as y cap. And our error is equal to y minus y cap. This is my error. Now this is for, like I said, that I have to minimize my error across a whole lot of observations. So suppose my observations are x1, x2, going up to xm. And for each of these observations, my target values or actual values are y1, y2, going up to ym. And I have my predictions, which are y1 cap, y2 cap, going up to ym. It's not right. Cap. Okay. So then I have my error one is y1 minus y1 cap. So my error I is equal to yi minus yi cap. So if I have to evaluate it for 30 days, because the month of April consists of 30 days, so I have my first day error, second day error, third day error, fourth day error, and all that. Now imagine my first day error is epsilon1 going up to epsilon2, epsilon3 going up to epsilon30 are there. Now first day, my predicted value was, let's say, 300 units. And the actual value is 320 units. So my error is 20 units. On second day, the predicted value is 310 units, but the actual value is 290 units. So my error is minus 20 units. So like this, it will continue. Now, as you can see, if I take my errors directly and add it up, what will happen is that my errors may cancel each other, positive, negative values, and thereby bring me some small value which is misleading. Okay. So what I need to do? I need to add them in such a manner which is smartly such that the cumulative error is giving me some kind of value such that the positives and negatives don't cancel each other. And to do that, what better thing we can have is by error total is equal to squaring them, because once we square a negative number, it becomes a positive number. So square error of total error is epsilon1 square plus epsilon2 square plus epsilon3 square plus it goes on plus epsilon30 squares, or maybe instead of 30 I can put it as a. Okay. So we'll put it as is equal to sum over I is equal to 1 to m epsilon I square. And this error is called as sum square error or SSE. I can say that, okay, if I take some square error, if I am considering it for 30 days, it may give some value. If I am considering for 31 days, because the number of days are more, it will give another value. Now, when it gives another value, I don't know whether that change in value happened because of change in number of days or because the prediction was different. Now, to bring them onto same scale, what we do is that we call what is called as mean square error. Mean square error. That is equal to some square error divided by total number of observations, M. It becomes mean square error. Now, mean square error is independent of how many observations were made. It brings them into a normalized scale of per unit of observation, what is the error I am getting. Then we can say that, okay, you have already squared it. Why not bring it into first order value? So we have RMSE, which is root mean square error is equal to square root of mean square error. Okay, so this becomes equal to square root of sum over I is equal to 1 to M epsilon I, which is equal to nothing but, nothing but actual yi minus yi cap, which is the estimate square. This is becoming root mean square error. So these are the different performance metric we use for evaluating regression. Now we have some other metrics. For example, we might be using something like called R-square score, which makes it independent. Now, as you can see, root mean square error. Suppose you are taking your height as a prediction value. The height can vary in the range of something like 100 centimeters to or 0 centimeters to, let's say, 250 centimeters. Now the errors can vary accordingly. Now suppose I am taking your quiz mark out of 10, then your error can vary in the range of that small value. RMSE is scale dependent. So depending if the scale is larger, the variations can be larger, hence RMSE is going to have a large value. If your scale is small, then your errors can be smaller, and hence RMSE value is going to be smaller. Now to make it scale independent, we use something like a R-square score, which is a statistical measure which takes it out of any scale. So if I say a R-square value of 0.8, whether it is for a quiz mark of 0 to 10, or it is a height of 0 to 250, it means the same. Whereas a RMSE of 2.5 for a height and for a quiz are not same. They have to be interpreted in the range of values in which that was observed. So we can use R-square score as a standardized measure, which makes it scale independent. Now coming back, so this is about the performance metric. Now coming back to our linear regression, where I said you have your independent variable X here, and you have a dependent variable Y. Dependent variable Y here. Okay. And then you are trying to draw a straight line. Now you are trying to draw this straight line. You are trying to arrive at the parameters of the straight line, which is our thing is Y cap is equal to theta 0, which is the bias factor plus or the shift factor plus the theta 1 of X. Now, how do I calculate from a given set of observations? What I have is I have X1, X2 going up to Xm. And for such of them, we have Y1, Y2 going up to Ym. So my theta 1 is equal to covariance of X and Y divided by variance of X. And theta 0 is equal to, we'll take it for the mean value only, is equal to Y mean, observed Y mean, actual Y mean, minus theta 1 of mean of X value. Please note, my notation of cap is for estimate or prediction, whereas the bar is for mean value. So when I have calculated my theta1 by finding the covariance of x and y, dividing it by variance of x, I have found my estimated value of theta1. Okay. Now, what I do is that how I find my theta0 is I take the mean value of y, the actual y values, and subtract the theta1 multiplied the estimated value of slope multiplied with the average value of x, and subtract this from the mean of y, I get my theta0. With this thing, my linear equation is ready. My linear regressor is built. Now for any given value of x, I will be able to predict my y value. Okay. Now if I have to take it for, instead of linear regression, I have to do it for polynomial regression. I have to expand my parameters and I have to come up with another mechanism. Now there is another way to do it, okay, which we will not discuss here, but you can study it on your own, or if you are curious, you can come and approach us. Sometimes I can explain it to you. There is another method called gradient, which you might have studied, gradient descent algorithm, which is an engineering optimization problem. So what you will do, you have your input and output, you take some initial theta0, theta1, and then you draw a line. And you find the error is large. Okay. Your data points might be like this. You find the error is large. Now, based on the error, you change the values of theta0 and theta1. Let's say this is initial, this is initial. So then now, based on the error, you make it theta0 1 and theta1 1. And you find that the error, let's say the line has now changed to something like this. Okay. Now again, based on the error, you try to change the values of theta0 and theta1 using gradient descent algorithm, and you may arrive at the final value of theta0 final, okay, and theta1 final, which will give you the minimal error, maybe something like this. Okay. Now, if I have a polynomial regressor, I may not be use the previous formula, but I can always use my gradient descent algorithm to arrive at my theta set so that I get minimum error. Okay. So this is how the regressors get built. But you have to keep in mind that all the classification algorithms can also be used for regression. Okay. Only thing is that they operate in a nonlinear manner. With this, I'll hand over the session to Supraja for running you through the working session. If there are any questions, I'll be happy to take it alternately. Supraja, over to you.
Yes. Any questions, anybody? Okay, so I will start. Yeah. So now we're going to do regression. So first, again, we have a data set over here. This is the calories data set, which I've taken from Kaggle again. So this contains different parameters, exercise sessions, duration, heart rate, body temperature, weight, and all these things. So before, like, what our task is. So our task is basically, our goal is to build a machine learning model. Which can predict, what can it predict? Can predict the calories burned. So that is our task. Based on whatever input features, our machine learning model has to predict the calories burned. So let us start. So again, the same pre-processing steps, data loading, then we are just checking the shape info. So you can see that we have 15,000 rows and 9 features. So yeah, we have the user's ID, gender, age, height, weight, duration, heart rate, body temperature, and calories. This is the target column. Now, after that, once we are done with that, We have checked all the data, we've described it. Now we're going to see the visualization again. It's the same visualization again. Histograms are being drawn for the numerical features. You can see the distribution of the user ID, distribution of the age, height, weight, duration, heart rate. These are already seen. Now visualization. So here, why we have performed this, basically we wanted to have so this is a heat map. This is what we call a heat map. So basically this here heat map, what it tells us is basically we have created a heat map to show the correlation, that is a relationship between the different variables. Let me minimize my screen. Yeah. If you can see, we have the different here. We have the left hand side, we have the user ID, age, height. So basically, we want a relationship between the variables, and these different red and blue colors will just tell us how strong or the weak the relationship is. Now, the question which might be arising in your mind is, why do we need this correlation? This thing. Why do we need? Basically, we need to know the relationship between the different variables, right? That is why we're doing the heat map. Now, why is it important? Why do we need to have? Why do we need to have this? And why we have different colors, red and blue? So what does it indicate? So I already told you that red and blue color will indicate the strong and weak relationship. So if you can see, red indicates the strong relationship, blue indicates the weak relationship. A higher correlation, that is 0.960, a higher correlation basically means a strong relationship between the features. And with this only, I will be able to select the most important features. Now, if you can see over here, with the heat map itself, I can tell which is the strong feature and which feature I will eliminate and which feature I will procure. So here I will have duration, heart rate, body temperature, and calories, because these all are the strong features. And here, if you see user ID, age, height, weight, no, we will just drop them. These are basically weak. This thing. So why feature selection is important? Because if we have all these features, the model will become too complicated and it might function slow also. So selecting the right feature will basically improve the accuracy also. That is why we are doing this. I hope this is clear. Any doubts in correlation matrix? Anybody? All good? Guys, okay. Yeah. Next, we have we are checking for the missing values, and then we are scaling the features. Again, I told you that if there is a huge difference, then it will become imbalanced, and then model cannot handle it properly. So we have checked for the missing values. We have removed the rows. If a row has multiple null values, we'll just drop them. So otherwise it'll cause some errors. Okay, so we have removed them so that there won't be any bias. Next is we have scaled the features, as I already told you. Scaling features we have done. Scaling feature means you have to always remember that mean will be 0 and variance is going to be 1. Okay, and scaling will ensure that all the particular values will be in the particular range. Now we have done done data splitting. Again, the split ratio is basically 80% of the training model, 80% is used to train the model, and 20% is used to evaluate the model. Now here comes the model training. Here we have the linear regression model. So here we are from sklearn. I have already told you this is a open source machine learning library from where we have imported linear regression. We have instantiated a linear regression model. So that is what you can see over here. And then once we have instantiated, we have to fit the model. So the fit, basically, what does this fit do? Basically, the fit will it will we'll use X-train and Y-train so the model will be using X-train and Y-train to fit the model, and then we'll evaluate. We are fitting it because the model has to learn the relationship between the features and calories. So we will find the best fitting line, like sir would have already shown you an example. For the other cases, here we are doing calorie. This thing we'll find the best fitting line that will predict the calories based on the given input. Now we are going to make predictions once. So when we are making the predictions, so basically we're using the trained model to predict the calories burned for the X test. So this is important because we have to compare the prediction, whatever the prediction is being made, with the actual value. So then only we'll be able to evaluate if the model is performing correctly or not. Then there are the performance metrics, which sir has already discussed, which is R square. Then we have the MSE, we have the RMSE. So these are used. Now, again, I will just give you a brief thing about what this R square is. So R square will basically tell us how well this model is fitting the data. Like 1 means a perfect fit. So 0.96 is a good value, right? What do you guys think? 0.96 is a good value or a bad value? Is the model fitting properly or not properly? You can at least comment in the chat box. Is the model fitting properly or not? 1 means the perfect fit. So is 0.96 a perfect, is good fit or a bad fit? Can I get answers in the chat box? It's a good fit. Yes, it is a good fit. So 0.96 is a good fit. And we have MSE. MSE is basically the average squared difference between the actual and the predicted. I told you, right? We had made a prediction. Now this prediction has to be checked with the actual. So that is MSE. And root of MSE is basically root mean squared error. Basically tells us how much the predictions deviate from the actual value. Now, why these metrics are important? If you would have seen that in classification, we had done other metrics, like we had the precision, recall, and other things, right? Here we are having these metrics. Why these metrics are important? Why a high R square? This high R, why do we need this R square value? A higher R square value is basically tell us how well the model is, how good the particular model is. And the low MSE will tell, low MSE and RMSE means that the model will have less error. Okay, it has to be noted. A higher R square value is needed. We need to procure a higher R square value, but a low MSE value. Okay, if we need to have less error, right? We can't have a higher error, then the model will not perform properly. So we need to have a higher R square value and a low MSE and RMSE value. Now, this is just the prediction, which is basically on how the actual and the predicted has done. So this is the linear regression model, basically, which has done a pretty good job for this, because you can see only like a particular, only if you see in the upper diagonal, the patterns, most points follow an upper diagonal, meaning the predictions are accurate. And there are like minimal errors. If you see, very less of them are deviated. Small deviations exist, but overall, if you see, it is a good fit, right? Overall, if you see, the fit is good. So predictions are, we can say, from whatever the data set we have done, we have tried to do regression, the model has performed a pretty good job. So if you see, each blue dot over here represents a data point. Each blue, you can see these all basically have overlap, but each of them, so x-axis has given us the actual calories burned. That is the true values from the data set which we have taken. That is the calories burned. And y-axis is basically predicted calories by the model's predictions, whatever the model has predicted, right? Those are present in the y-axis, and x-axis is basically the predicted calories, whatever the model's prediction. And this is the fit we have got. So using scatter plot, we have compared the actual versus the predicted, this thing, using a linear regression model. So this is it. Okay, I think it was simple. Any doubts anywhere, please ask me. Anybody? Any doubts? It's clear? Abhinav?
I think no one has any doubt. It's fine.
Okay. That's it.
So anything do
I
you
have
want to
shared
add?
this in this thing, in the Teams chat, so I think everybody can just have a look through. Yeah, that is it.
So I hope everyone enjoyed today's sessions and got to learn a lot of new things. We'll be posting all the material on our website by the end of the day. You can also access the files through the Teams chat. The session has been recorded and you can also access the recording on the website. Along with that, as I instructed in the start of the session, we'll be posting an assignment which has to be submitted by Wednesday end of the day. Please adhere to the instructions given in the assignment. And if anyone has any doubt, feel free to reach any of us out and through mail or through WhatsApp. Anyone has any doubts or want any clarification? Okay, so we'll end the session now. Thank you everyone for joining. Thank you, sir. Thank you, Supraja, for a wonderful session.
Thank you.
Thank you very much. Bye.
Thank you, sir.